Okay, so last lecture in our foraging series. Um, Looking forward here, we've got the reading assessment and the comprehension exercise for this unit. Then due this weekend, given this is the last for that, and then next week. The Unit G is only 2 lectures. So then next weekend, we've got then the reading assignment for the Unit G, as well as the Canvas assignment for Unit G, then due a week from this Sunday. Also due this upcoming week, November 7th, I think, is your selected organism in context. You work with your groups, not looking for much, just 1 to 2 paragraphs, identifying which animal you're looking at, why you've chosen that animal as a good example of something that there might be behavioral consequences of living in or around humans. And no animals in captivity, no zoos, no pets. If you're having trouble identifying the animal, then including a photo would be a nice thing there. We can help you with that. If you submit it, there's the rubric for this is pretty light. So this is one of those things where we try to give you credit. It's more of a to turn it or not. And then give you feedback on your selection. So you definitely need to tell us the animal. You tell us the context, like what motivates the selection of this animal. But we don't need a whole lot more other than that. And then and immediately once you start turning them in, then might start getting feedback from me and from the TAs. So that saying like, hey, I think this is a good direction. Maybe this is a little too ambitious. Maybe this is a little, like, you don't want to ask a question that sort of has already been answered. Like, you don't want your study to just be describing something that's already understood. So, try imposing a question that is trying to explain an observed pattern, which may or may not be there, but doesn't have a good explanation for, or maybe propose change and how that might, potentially change behaviors of these things, so on. So things like that, and there could be, sometimes what happens is things drift away from behavioral. We'll see some of those, like it ends up being more, like you could have hypotheses that relate to the population demographics of the animal. That's fine so long as the underlying hypothesis that would predict those changes in demography has something behavior to do with. So, they're moving into these areas because of some color signaling connection or something like that. So it has to have some link to behavior. But as you can see, behavior is pretty broad. So there's probably a lot of ways you could do that. The key thing is something that helps build up to asking a causal question, proposing a hypothesis or hypotheses to that causal question, and then proposing an experimental design for testing that hypothesis and giving us the predictions corresponding to that design relevant to that hypothesis. So that's what your final project will be, but this is providing you the foundations to build that. All right, so that's what we got looking forward for this weekend and coming up to next weekend. Any questions? Okay. All right, so let's get back to foraging. So we left the last time talking about the marginal value theorem, which is the behavioral ecologist version of the equimarginal principle from economics. And so we were talking about food sources there where the choice is not whether to eat or ignore the source. That's today's topic, but how long to stay in the source. So you can go from source to source to source. And when you make these how long decisions, then that's what we refer to as patches, making decisions about patch residence time, how long to reside in a patch, where a patch is sort of a clump where you can hang out in that clump. And eventually you leave that clump almost always before the clump is fully depleted. So trying to explain how are animals leaving early? Why are they leaving early? Why don't they just completely deplete each one of these patches before moving on to the next patch? That's what we're trying to understand. And ultimately, no pun intended, what we get to is that the strong hypothesis that seems to explain the residence times we see in nature are that animals are behaving consistently with a hypothesis that they're rate maximizers. So they're not calorie maximizers. They're not trying to do some other strategy. I mean, there could be other strategies that also have the data that we see. but at least one that keeps showing up. And that's the reason why it's called optimal foraging theory. This theory shows up in, it makes predictions that seem to hold across multiple different contexts and multiple different animals stressed in different ways. And so that's why it kind of builds up to the name of theory, optimal foraging theory, or OFT. And the marginal value theorem, a big part of optimal foraging theory, trying to explain why animals leave early, don't stay for the whole time that they could. And so with that in mind, we painted this picture of diminishing marginal returns. So really, when you look at this curve, which is how many berries do you get out of the bush for the longest time you're in the bush, how many larvae do you parasitize if you're a parasitoid, as you're in a clump of larvae, and so on. Well, we think about the derivative of this, about the rate of change of this, where the highest rate of changes are here and the lowest rate of changes are here. And so that's what we mean by diminishing marginal returns. It has an always increasing rate of change, but it's decelerating. So the rate of change is getting lower, even though the actual gain is getting higher. And so as the bang for your time bucks, because that's what animals don't have currency like we have. They don't, really, we're animals, of course, and so we do care about time, but we have jobs and we have turned time into money. We spend a certain amount of time doing a job, and then we convert that into cash, and that cash is a stand-in for time. And so when someone says, $10 for this particular thing, what they're really saying is work for $10 amount of time, and then I'll give you this. We've just created this middleman, we've created this like ATP that we use as a middleman, but really we're trading in time. And so when we look at animal foraging, we're looking at the fundamentals there, how they trade in time, because we don't see currency that they use. But it's the same idea. So over here, they're saying that, for the first dollar I spend, I get a lot of benefit out of it. But for the 20th dollar I spend, I don't get as much benefit out of it. So if this was a Netflix subscription, this is like the ad-free model. This is maybe the, mostly ad-free model, and this is the total, or sorry, this is the with ad model. This is the mostly with ad model, or some ad-free, and this is the totally ad-free model. And maybe not a lot of people go to the totally ad-free. Maybe Amazon Prime was a better example. So there's not a lot of people who maybe have the disposable income that they or so in other words, they may not be in the condition where the value they get out here balances out all of the other things they could be spending that money on. And so they end up dealing with ads. That's the same thing that these animals are doing, is they're saying, it's just not worth my time to stay in this patch, so I'm going to go try another patch. That's what we're trying to explain. And so that's the kind of the picture we're painting here. And how do we predict that time? And so we used this marginal value theorem, where we said, well, this down here, this was our Holling's disk equation. If we maximize this thing relative to time in the patch, then we get this relationship where the derivative, so the change over handling time of the patch, ends up equaling the rate of return you get back from the whole environment. So again, this, if you think about in terms of your own personal life, then if you had ways to measure a unit of happiness, then you could say, well, all the things that I invest on, so I invest in maybe a video game subscription, a TV subscription, food, all of these things, for every extra dollar I spend on them, they give me a little bit of extra happiness. And you eventually, though, stop choosing to spend your next dollar on one, because its returns diminish, and it becomes more effective to spend your next dollar on another thing. And so over time, what happens is all of your investments give you the same happiness per dollar value back across all of your investments. But because some of them are richer than others, then that means that you might spend more on this subscription and less on this subscription, and way more on food or whatever. But across it, what economists have shown is that generally speaking, the way people allocate their money balances out the happiness to next dollar ratio. And that's all this is saying is that, but now we're measuring happiness as a proxy for happiness in terms of calories. So when we're focusing just on foraging, we're saying that whenever an animal is in a food source, it stops eating that food source when the calorie per time immediate returns end up equaling the calorie per time returns from all of their investments. At that point, stop, because any further exploitation of this patch, it's better off just leaving the patch and getting rewards from the environment, because the environment will do just as well as this local patch. That's the marginal value theorem. And that's summarized graphically with this curve. If you know that for this patch, these are your rewards, so they have high marginal returns initially and they flatten off over here. If you know the search time in between patches, then you just plot the search time over here on this negative axis, and then you take a line, it's like a barn door or whatever that swings down and hits this thing hinged at this point, and that point of tangency with that curve tells you the optimal amount of time you spend in that patch. So when patches are very close together, then that means that you get a lot of reward from the rest of your environment. The rest of your environment is cheap. So at that point, you're not willing to spend much on Netflix because Amazon Prime and all the others are so cheap that you would just rather balance your money across those. But as the rest of the environment gets poorer, as your other options get more expensive, as you have to spend more time searching for another option, then you end up spending more time in the options that you exploit. And that's what we're saying here. So they spend more time in the same patch if there's more distance between the patches, less time in the patch if there's less distance between the patches. And you can test for this. You can put them in natural environments or in laboratory environments and see how long they exploit patches and manipulate the time between patches and see if it goes in this pattern. That's the marginal value theorem. Questions about this idea? Okay. Fundamental idea. Person who came up with it, Charnov, actually spent most of his career at the University of Arizona down the road from here. So it's kind of fun, I think. So we can generalize that across multiple types of patches. Again, this could be like, Netflix, Amazon Prime, food, or something like that. You can imagine different options and how much time or how much money do you invest in each option? How much time do you spend in each patch? Well, like I was just saying, across each patch, the point where you stop and leave that patch to go to other patches, that will be at a point of tangency, at a slope, at a marginal rate of return that will be the same. It'll be in parallel with the slopes at the other ones. So this line is parallel to this line, is parallel to this line, but because this line has faster diminishing returns, or it's a poorer patch to begin with, then it doesn't take very long for you to hit the same point that you spent a lot longer in the rich patch. So you get different times, but the marginals are equalized across it. That is the marginal value theorem. And that is summarized up here. I used a different notation up here. I'll probably go back and change these slides so that this G prime is a DG, DH. I wasn't initially educated. My undergrad education wasn't in biology, so I just had to ask biologists if I was an undergraduate in biology, would this be the notation that would make sense of all that? So I asked my wife, who does have her undergrad in biology, and she said, I would do DGDH. So that's why I switched it, but I forgot to switch it there. So that's why it's DGDH up here. But it's the same thing. It's just a different notation. So this is just saying across your patches, then you equalize the happiness, the calories you get per the next dollar, next unit of time you spend. And they get equalized across all of the patches in the environment, the equimarginal principle. The consequences for that, the predictions for this are down here. If you have a poorer environment, so everything gets bad across the patches, then that's going to mean that if you have the same patches, you're going to spend longer in each patch. The other side of that is for any given environment, if you look across the mixture of patches, you're going to spend more time in the richer patches. So that's one set of predictions. But a lot of times ecologists flip this arrow. So when we can actually then make an inference about the environment. So sometimes you don't know how good or bad things are right now. So you go out and you watch some lizards foraging, or you watch some birds foraging, and you see how long they spend in particular patches. And you can actually figure out the density that they leave. So there's this giving up density, which is related to this time. And they basically will leave the patch when they get to sort of equal density of arrivals within the patch. And so you can measure this giving up density, and you can see across like this bird, I'm going to follow it, and I'm going to see it. This patch, it spent 10 minutes in there, and that seemed to reach a density of this many encounters within the bush. So you can watch how many times it finds a berry within the bush. And then you watch in this patch, you see how often it finds a berry within the bush. And you start noticing that there's a particular density of berries that is when the bird ends up leaving and moving to the next one, and they get roughly the same, roughly equal. So you estimate what that giving up density is across the environment, and you maybe come back there in a week, in a month, in a year, and do that same exercise. If you find that the birds in that population that used to leave at a particular density now stay in the patches longer and leave at a different density, then that might mean that something's happened in that habitat where they now have a harder time finding food. So maybe there are fewer patches around. Maybe they are expending a higher cost in order to travel. And so this maybe explains that it might be a poor environment. Or if they start leaving the patches a lot sooner, maybe something has enriched the environment. So maybe it's a seasonal thing. Maybe it has to do with some landscaping that was put in or something else like that. So not only can we make inferences about animal behavior, if we study the animals, we can make inferences about the environment. And people do this. And so it's a nice example of G by E here, where we observe a phenotype. We observe how long they spend in patches. And we know that phenotype is the product of, the animal, the genes, and the environment, how sparse things are. And knowing that phenotype could tell us about the animal, but if we fix the animal, like we're always watching these birds, then it can also tell us about the environment. And so I think it's a beautiful example of ways in which we can use animals as indicators by better understanding their behavior. All right, any questions about that? About flipping things around and learning about the environment by studying the behavior? And people do this too. Like, I'm not just making it up. You can find papers where people use giving up density to then make inferences about patterns that are happening in the environment. Okay. All right. So we also talked about variance, which we'll get back to because it ends up tying really well into the back half of this lecture. So that's why I wasn't so worried that we didn't get it covered last time. Okay. So today, we're focusing on the other half of this. So we talked about patches last time. We're talking about prey this time, lumped units of food. So, we watch this quail. One of my favorite examples is quail. And, they go around and they're ignoring a lot of different little critters that, mealworms and other things that they eat that it can find there, but they're eating some others. So we can ask these questions, which prey items are being eaten? So that's a descriptive question. And we ask the why question. Why is it choosing these prey items? So which are being eaten, which are being ignored, and the causal question of why. That's what we're focusing on here. So we're not talking about how long do they stay in any one place. Now we're focusing on the case where if in order to get any gain out of it, you have to spend a certain amount of handling time, and that's it. There's one handling time and one gain per prey item. So we refer to that as being lumped as opposed to being patchy. So this is the optimal patch choice or prey choice problem. Which prey do you pick? And so that is, in order to help understand this, the early models were the prey model, so to speak. And so there's Charnov, the guy who spent a lot of his time at the University of Arizona. This was sort of, there are a lot of Halling, Halling's disk model had a big influence on Charnov, and then Charnov formalized this prey model, which we're going to summarize here today. Okay, so the idea here, the cartoon idea is imagine you've got a bunch of different prey items that are out there just peppered throughout the environment, like on the ground with that quail. And I've colored them as opposed to 3 different types. So you can imagine this is like a mealworm, a seed, and a berry or something like that. Different things you could find on the ground. And so for these 3 different types, we gave each an average gain. So on average, when you eat a mealworm, you get these many calories, and an average handling time. You can't eat a partial mealworm, you got to eat the whole thing. And so on average, it takes 4 seconds to ingest the mealworm. So you get 40 calories for 4 seconds. And that's all these purple ones. That's what that represents. So different types. So this is a seed, so it might have different gain, different handling time, but all the red ones are seeds that are very similar to each other. So that's the picture we have here. And then we imagine you get your predator comes in here, and it then starts moving around, and it encounters these different items. And as it encounters them, it either stops and eats them and pays the handling time, pays the cost, and gets the benefit, or it ignores them. So we've got examples over here where it decided to eat this one, but over here, it decided to ignore this one, ignore this one, ignore this one, and then come and eat this one. So you might have cases where it encounters a red prey type, and it ignores it sometimes and eats it other times. So trying to understand these patterns, that's the goal here. Okay, so that's the setup of the problem. And so we want to try to build a prediction based on the gain and handling time of each one of these prey types and the search characteristics. So how easy it is to find those. So it's very similar to what we did with the marginal value theorem. And in fact, this is going to be a discrete version of the marginal value theorem, but we don't have functions that are smoothly varying. We just have these lumped prey items. So we're going to turn to Halling's disk equation again. That is our go-to for these simple optimal foraging theory models. And as a reminder, we view, kind of double-clicked there, but as a reminder, we view this as an opportunity cost rate. So what you get from the environment is the opportunity cost of spending more time in any local option. So if you know that over like all of your choices or how you spend your money, like again, Amazon Prime, Netflix, food, Uber, Eats, et cetera, all these different ways you could spend your money, then there is a background happiness you get from your portfolio, from what you've chosen to spend on. And if any individual option is not providing you that same bang for the buck, that same gain per dollar, then why leave that in your portfolio? The rest of your portfolio is giving you that amount of happiness per dollar. So you may as well stop spending on that because there's an opportunity cost. You may as well spend more on the things that are giving you more happiness per dollar. And that happiness per dollar from your background environment, that is this, but it's in terms of calories per time. But it's the same basic idea. This is our background threshold that we compare everything to decide, is it worth it or should we ignore it? That's the basic idea behind the prey model, which is just an extension of the idea in the marginal value theorem. So we're going to think for every prey that you come about, so this quail sees this prey, and it has some way to estimate the gain it's going to get out of that, the calories it's going to get out of it. It recognizes that's a mealworm. And so that's the benefit that'll be received after handling it. But then this is how much time it's going to pay in order to receive that benefit. You have to spend money to make money. It's kind of the idea here. Or they're just 2 different currencies. This is happiness and these are dollars. This is calories and this is time. So is it worth giving up this amount of search time to gain this amount of calories? That's our question. And the prey model is just going to compare the value we get from this proposition to the value we get from the background environment. And I've already kind of asked this, like, how do we determine if this cost, H, is a good price tag for G. Well, what determines what's fair? It's the background environments. It's how well you've been doing so far. So if you know that so far, every second of search time, you've been getting back 30 calories, and this is going to take you a second to eat, but is only going to give you 10 calories, then probably we shouldn't eat it. We should ignore it and look for something else, because if we eat this, it's going to bring down our background happiness rate, our background generation of calories. And that's what we're going to use here. So we're basically just going to compare this ratio, which we call profitability. So, and that's not my term, that's just what they call it in the prey model. So in the prey model, every prey item is sorted by its profitability, which is the calories you get from the item, the net calories. So it takes some calories to eat it. We're going to subtract those off. So the calories I get minus the calories that I need to chew it up. So the net calories I get divided by the handling time. So how long do I have to sit here munching on this thing before I can return to search? The handling time there. That ratio, that calories per second ratio, that's basically a power ratio. Remember, this is energy per unit time, that's power. So how many watts of energy, how many watts of power do I get out of this thing compared to how many watts of power do I get out of the background environment? How many calories per second? So that's the profitability. And so what we're going to do is just sort all of our prey items and come up with a cutoff value. That's the prey model. So if you had N different types of prey, mealworm, seed, leaf, whatever, you'd come up with a bunch of these different types of prey. For each one of them, you can say, what's the average calories I get per type of prey? What's the average handling time to actually ingest that prey? And then I can give a profitability to each one. This won't be sorted by calories necessarily, because some things that give me a lot of calories might require me sitting there for a very long amount of time to actually eat it. So if it's very high handling time, it will be maybe very low in the ordering. But if it is very low handling time, even if it's low calorie, if it's really low handling time, then it might be very high in the ordering. So these are your cheap, you could almost call these empty calories here. So this also maybe suggests, issues with, if you've been, if you have a prey choice algorithm in your head that's been adapted over evolutionary timescales, and then suddenly you're thrown into a food environment with a lot of so-called empty calories, that this is why you crave empty calories, is that theoretically speaking, natural selection is driving animals like us to optimize our rate of gain. Well, how do you optimize your rate of gain? You really like empty calories. You like those sweet things that are very quick to eat. Those come very high in the ordering. Whereas the salads and so on, very little calories. The stuff that sloths eat, they would fall very low down here. So this is where this is why you don't ever eat salads at the end of a meal. If someone provided a whole big meal for you and then said, and for dessert, here's a salad, no one would eat it. That's why they force you to only consider the salad up front, because our psychology is shaped by this. The only way you'll eat a salad, the only way you'll sort of be hungry for a salad is if the salad is the only thing in the ordering. And so you eat the salad first, it bulks you up a little bit, and then they bring the higher profitability items in. And then that way, there's always room for Jell-O. There's always room for high calorie, low handling time things. That's the prey model. So sort them all, and there will be a cutoff where anything above that cutoff you eat, anything below that cutoff you don't. And that cutoff is the background rate of return from the environment. So if you know that on average, for every minute of searching, I get this many calories, turn that into a threshold, and that's your profitability threshold. So if the environment gets poorer, if things get harder to find, this threshold will get moved over. It'll get moved over from the middle here to this direction, to the right, and you'll start eating more in your diet. If instead these high profitability items become more plentiful, then you're going to get more overall background rate of return from the environment, and this is going to move left. and you'll start eating only the highest profitability things. You'll start excluding more things. And so that shifts around with how rich the environment is. And that's something that we're going to call the 0-1 rule. So I think we've got this, this will be mentioned here in a second. So this idea that there's no partial preferences. Every prey item under the prey model, every prey item is either eaten or ignored. That's one thing. So that's the so-called 0-1 rule, which I'm going to summarize, and I'll list that term in a second. So this strict partition, that's the 0-1 rule. Either eat or ignore. There's no partial. There's no flipping a coin. That's the one thing here. The other major prediction is that what you eat only depends upon the encounter rate with the things you're already eating. So if you take a low profitability item the animal's already ignoring and make it more plentiful, it will keep ignoring it and it won't change what it's eating. But if you take an item that it's already eating and make it more plentiful, then it will stop eating more things. So it'll start ignoring more things. That's the other key prediction of this prey model. All right, so I'm going to step through all of that, but any questions about this general outline of the prey model and an opportunity cost being the fence which separates the eat from the ignore? Okay. So, changes in encounter rate, that's all I'm saying here. Only these encounter rates matter. These encounter rates don't. You make these more frequent, you'll eat less of these things. You make these more frequent, nothing will happen. So that is one thing. That's what I'm saying here. And this accumulated gain is an estimate. So there's a mechanism here where if you, this is the optimal solution, but there's actually suggestions that animals can estimate how much, how full they are and how long they've been foraging. So if an animal knows its accumulated calories over how long it's been foraging, there could be neural mechanisms that keep track of that. And those neural mechanisms can help it make these decisions in a dynamic way. So if you starve the animal, it'll have very low calories, even though it's been foraging for a long amount of time, and it'll become a generalist. But if that animal has had a lot of food in its history over a very short amount of time, it will become a specialist dynamically. And so the thought here is, although we're describing a static diet, the thought is that maybe animals can actually estimate this on the fly, and that helps them make dynamic changes in their diet based on their current hunger state. So that's the other prediction there. So how well does this work? So this is an example. They gave a mantid, and these experiments with these mantids are kind of fun because they sort of snap at their prey. So you can increase handling time by sort of just making food farther away from the mantid. So there's all sorts of cool experiments you can do with these mantids. And so the idea here is you can see they've got, they starve the mantid for different amounts of time. And then they see at what point do they stop eating these flies that are presented based on the starvation time. And this prey choice model predicts this line here. And these confidence intervals are what's actually observed in the mantid. So it shows that using that ordering that I had there, you can actually build these predictions and test it with these animals. And you find out that for many animals, they fit the predictions very, very well. You starve them more, they become more generalists. So basically this weight of food eaten here, this is like my ranking. And this is like the threshold that's separating the things that ignore from the taken. And so the more starved you get, the poorer the environment gets, they start becoming more generalists. So that's the example there. So that is a pretty good prediction. The other way we can test the predictions, this clever experiment here, where they've got a box, a cage that you can put a bird in, and a belt here. And so this belt can go back and forth, and you can change the spacing of mealworms on this belt. And the bird gets to sit on this perch here, and look through this tiny little gap at the belt. It's a little bit like one of those sushi places. It's got the sushi coming down the belt and you just grab what you want. That's what they've built with these birds. And so with that, then they can change the value of the things on the belt and the spacing of the things on the belt, and then see if you can predict what things the bird decides to go at and what things the bird just allows to keep going down the belt and ignore. So how did they set this experiment up? So I think this is just me, setting up this. So we've got a cage, we've got a perch with a bird on the perch, you got the conveyor belt that can be replenished by experimenters. Okay, so they've got these experimental treatments. So there's two letters here, the red letter and the blue letter. The first letter, the red letter here, it's got V, L, and M. So this is the encounter rate for the high profitability type. So we've got very low, so you hardly ever see it. Big spaces between that. Low, which means you see it a little more often than that, but still not very often. Moderate, you see it pretty often, and then high, it's like always in view of the bird. It's there very frequently. So you've got these encounter rates for the high profitability type, and then on the blue, that's the encounter rates for the low profitability type. What do we mean by high profitability, low profitability? They took a mealworm and they just cut it. And so, mealworms have got these segments, a segmented body. Anushka, one of the TAs, she does experiments with me with these ants in Australia that carry things up trees. And she's very familiar with this. So we'll have mealworms and we'll cut them into different segments and we give the ants small mealworms and large mealworms to carry up the tree. Same idea here. An 8-segment mealworm has got a lot of calories in it. A 4-segment mealworm has got less calories in it. They did a test in a pilot study to show that the handling time was roughly the same for both of these mealworms. So handling time's the same, calories out is different. So that's what makes this high profitability and this low profitability. So you've got two different types, high profitability and low profitability, that can be encountered at two different rates. And this sets up testing the prey choice model. Okay, so let's see how they do that. So we've got these treatments here that I just explained. And then here are the actual encounter rates with the large prey and the small prey. So this is just echoing these things here. And then what these translate into is a fraction of the large and small prey. So to here, when they're equal rate, then they see 50-50. Whereas down here, when the small prey are twice as often, seen twice as often as a large prey, it's 33-67. So that's kind of the setup of these things here. So the key groupings that I want to highlight here are these top two rows. We have low encounter rates with high profitability prey. But otherwise, the same encounter rate with low profitability prey. The way this experiment's set up then, in the bottom three groups, we have high encounter rates with high profitability prey, and then low matched or higher encounter rates with low profitability prey. So see what they're doing here. They're testing these predictions about whose encounter rate matters. So up there, they made sure that we're going to make the high profitability have a low encounter rate. And in theory, then you would predict that there would be no preference and they would just be a generalist, because you always eat the high profitability if it's available, but if it's not available, you eat the low profitability. But then down here, under these conditions, then they're going to say, well, you always accept the high profitability prey. That would be the prediction, the main prediction of the prey model. But because the high profitability prey is so frequent, then you ignore low profitability prey regardless of how often they're coming. So the thought is that you can find an encounter rate in between these that gets you from the blue box to the yellow box. And if you go from there to there, you're gonna switch the bird from generalist to specialist. That would be the prediction from the hypothesis that comes out of the prey model. And so that's what we're gonna try to test, and we're gonna see what happens here. Okay, so let's then look at some of these results. So in this treatment here, we have a high encounter rate with high profitability prey. So if we look at this, here are the encounter rates that are being presented by the experimenter. So here are the proportions here. Prediction is low profitability will be ignored. So we look at the results and that prediction holds. And so these are 5 different birds. They're named by their color tags. That's why you get BWRO, et cetera. And what we end up finding is that the percentage of prey in the diet, at all encounter rates, all birds generalize. Sorry, so this is for the yellow portion. So in this case, they eat everything. So that's what we're saying here is that all of these are close to 50. This is describing their diet. They encounter them 50% of the time, and so they eat them all. So in their diet is balanced between the 2 prey types. But then if we flip to the other half of it, we also match our prediction. So here across those 5 birds, then you see all except for, there's a couple of these 2 outliers here, but generally all of these here all show a significant preference for the high profitability type. So they seem to be specializing on the high profitability type once you're at a sufficiently high encounter rate with the high profitability type. And the low profitability encounter rate doesn't matter. So, that it's at the point where you're eating only the high profitability, you're ignoring the low profitability and ignoring how often you see it. That's the thought here. So it seems to match those predictions. All right, any questions about that experiment and those results? Yep. That's a great question. So yeah, I mean, like the physiology of the bird knows that threshold if this is right, but the experimenters don't know that threshold. And so the experimenters predict that there will exist a threshold. And a lot of times these go through, well, you have to go through a range that your kind of background about the physiology of the bird thinks that if there is a threshold, you'll probably hit it, but you may not hit it. So if they wouldn't have found that threshold, if they were generalists throughout all of this, then there would be a discussion at the end that would say it's also possible that we just never hit that threshold. And a future experiment might try even more extreme encounter rates, and then maybe we would eventually hit that threshold. But so you could say maybe they're lucky here. What we also don't see is it's a possibility that the grad student that was doing this project did a bunch of other encounter rates that they didn't publish on, and eventually titrated and found, aha, this is the threshold. But there might have been a lot more work before this paper. And then because the paper, they just wanted to write a 10-page paper, they didn't publish all that extra stuff because this ended up showing the result that they were testing for. But it's a great question. How do you figure out this threshold? It is effectively arbitrary or unknowable without kind of titrating to find it. Any other questions about this result? Other thing I want to highlight is that none of these are at 100%. So the prey model predicts 0-1 rule, 100%. And at the time, this was a real success for the prey model. This is one of the first studies that show the prey model has predictive power. But it clearly isn't everything. And that's going to get to the bottom half of this lecture. What are the other things? So our goal in science is to explain unexplained variance. This shows that the prey model has the ability to explain a large fraction of variance in prey choice that we see in nature, but not all of it. So, that brings up the question of how do you explain why sometimes these birds, go back to chance, almost even prefer the other ones? Is that just random? Is that just bad luck? And then some of these birds have clearly a preference for the high profitability type, but it's not quite as strong as you'd think if it's a 0-1 rule. So what's going on there? Yep. These are the names of the individual birds. Oh, these here. So this is the I've got the red is the encounter rate with the high profitability prey. The blue is the encounter rate with the low profitability prey. So this is very low encounters, moderate encounters, high encounters. I might have got that backwards. Yeah, so I can go back. There's a slide back here where I define those. So these are the 5 treatments, and these are how they're defined. And then so blue is low profitability and red is high profitability. Okay. Other questions about that? Okay. So seems to fit pretty well, at least initially. Okay, so, but it doesn't fit perfectly. And so how do we explain the rest of the variance? Well, it turns out foraging is complicated. Lots of things are involved. We've already seen some examples of this, which I'm going to give tip a hat to, and a couple of things are gone over here. But basically, one of the things that seems to help explain partial preferences, violations of the 0-1 rule, and totally skewed choices. So there are some animals that just do not appear to order things by profitability. They seem to have some ordering, but that's an ordering which does not appear to be gain over time. And so where does that come from? And what's been very successful in understanding these violations or these deviations from the prey model are models based on constraints. And so I'm going to talk about a couple of those right now. And so we started talking about this one last time, but I phrased it in terms of variance, not in terms of constraints. But so to a reminder where we left off here, so this is a yellow-eyed junco, and they're the model organism here that we're focusing on a bird that, in order to survive the cold night, has to eat enough energy or have to eat enough calories by the end of the day. So there's two constraints here. There's a time constraint and an energetic constraint, but the time constraint is the thing really driving everything. If it doesn't get a certain amount of energy, it has a physiology that keeps it warm at night when it is not foraging. And it needs a certain amount of fuel in the tank to keep the heater on all night. And if it doesn't have that amount of fuel in the tank, the car is going to go cold and it's going to freeze to death. So in the morning, it's fine. It's like it's foraging out, but by the evening, if it doesn't have that much fuel in the tank, it's got to find a refill station ASAP. And so that could be driving its behavior. And so, I had the fuel analogy here, but for it, different seeds, some have consistent caloric and intermediate caloric content. So some are just always roughly 50 calories. But there's other seed types that sometimes are just hollow shells. They don't have anything in them, but sometimes they're bountiful. They've got lots of different, lots of high calorie, high calorie seeds. So you'd maybe until you crack them, you don't know whether they're high calorie or no calorie, but they can be very high calorie. And then another side of seeds is just consistently intermediate calories. So that's the thought here. There's ecological relevance. We think the junco does have to solve these types of problems in nature. So it becomes a model organism for studying risk sensitivity. So again, we started talking about this last time. Experimental manipulation here is you take yellow-eyed juncos and you starve them for an hour, or you starve them for 4 hours. And then in both cases, you give them like a Skinner box where you say, okay, on this side, if you hit this button, you're going to get 5 calories or whatever the unit ends up being, 5 food units consistently. Every time you hit this paddle, you're going to get 5. But this other paddle, if you hit that, half of the time you're going to get nothing. And the other half of the time, you're going to get 10 calories. And so you can give the severely starved junco the choice, or the moderately starved junco the choice, and see if there's a difference in their choices. At some point, do they choose the one that has variable rewards? That's the question here. So you might predict that this junco, if it's average, like how well it's doing right now, is above its survival threshold. So imagine this is how much energy it has at the currently. And so we're saying after an hour, it's above its survival threshold. But after 4 hours, if it stays this way, by the end of the night, it's not going to survive the night. So this threshold here, that's determining whether it has enough energy to survive the night. And so the thought is, since this one's already above, then maybe it'll take the consistent rewards, because that will keep it above. But this one, if it takes the consistent rewards, maybe that isn't enough to get it above. So it'll go for the variable, because if the consistent's not enough to make it survive, at least the variable has a chance of getting over there. That's the idea behind this. So the way we model this is we say, what are the distributions of outcomes over foraging choices? And we can say one seed type always gives 5 calories. And so let's say this is our energetic threshold. And wherever the bird is, if you eat that 5 calories, you'll be over that threshold. But the other one, so the bird is sitting right here, has a seed that's either 0 or 10. So we got two distributions here. These are our variable seeds are in orange, our consistent seeds are in green. And so the risk averse forager is going to prefer the consistent seeds in this case because it keeps them over, it pushes them over the survival threshold. Why risk it? You go for the consistent rewards, you can pay your rent, everything's fine. Yeah, you theoretically, there is a universe in which you could do really well, but there is another universe where you're going to die. So you may as well say, I'm just going to go, I'm going to, what we're going to talk about, I'm going to hedge my bet. So I'm going to take a hit in reward and potential reward in order to get certainty of survival. So that's what we refer to as a risk-averse forager. But so mild starvation, we would expect a risk-averse forager. But on the flip side of that, if you're starved, if you're the after 4-hour junko, then you're down here. And adding 5 calories does not get you over your survival threshold. Adding 10 calories does. So in this case, you might actually be a risk-prone or risk-seeking or variance-seeking forager, where you're going to prefer the more variable options. And so if neither option escapes the risk, the variable option minimizes it. This is weird behavior, right? At least it seems weird. Why would you ever prefer a variable reward? But this is, this is my intro to this last section of the lecture. Constraints make animals do weird stuff. And this is one of the things is that, logically, it seems counterintuitive that you would ever prefer a variable reward. But you have to think of it in terms of distribution. It's not in terms of the 0 you sometimes get. It's in terms of the possibility of getting a 10 and that the consistent reward is never enough. And so that's why you might seek out variable rewards. And this can then, both of these have the same mean, but as we're going to see here in a second, this can actually make you sacrifice mean. So optimal foraging theory, the prey model, it would suggest everything's determined by mean. And if the mean over handling time is better, that's the one you prefer. This is suggesting that you could get shifts in prey choice based on variation. And this standard deviation, this variability, is nowhere to be found in the prey model. So you can get violations of the prey model ordering due to this threshold effect. All right, any questions about this idea that hungry animals may actually start preferring variable rewards? Okay, so we can generalize this idea by saying that there's just like a bell curve of outcomes from the end of the day. So the central limit theorem says that if you eat a bunch of things, you add all those calories together, and the distribution of calories at the end of the day is going to look like a bell curve. And so that bell curve, this we're saying here, is that you might have a bell curve that puts you here, which means that if the mean of the bell curve is less than your survival threshold, then you would like to make this as wide as possible because you want the tail of this distribution, those rare times where you get really lucky at the end of the day, you want to make them less rare. And most of the time, you're not going to survive. But there at least is some possibility you're going to survive. And if you can make this as wide as possible, then you'll reach your so-called stretch goal. So that's what the financial people call this, a stretch goal. So when they're, so if you're investing in stocks, this is the rate of return you get at the bank. So you could have put all your money in the bank, but you didn't. The bank is going to give you a 1% interest rate. So you better invest in stocks that give you at least a 1% interest rate, because if you don't, then that's just a really poor investment. So not reaching the bank's interest rate is like dying in nature. And so they, have this term stretch goal, which has to be that my portfolio, the average return for my portfolio of stocks is less than what I get from the bank. But I can then rearrange my portfolio, reinvest so that I maximize variance. And that will mean that I'm going to have sometimes have a really low performing portfolio, but there's at least a chance I'm going to have a really high portfolio. And that's again, stretch goals, and why you might maximize variance. Questions about that? All right, when times are tough, maximize variance. When times are not so tough, when your behavior, your average behavior, is actually above your survival threshold, it's exactly the opposite case because you don't want anything to cross the threshold in this case. So in this case, you want to squeeze this thing together. And so in that case, you're going to start looking for rewards that have as little variance as possible because that keeps you over this threshold that makes sure that there's no chance that you're not going to survive the night. So in that case, you're going to be risk averse and minimize your variance. Now, the interesting case that comes is, I mean, I find it all interesting, but I know sometimes may not be as interesting as I deliver it. But a more interesting case, at least to me, is this bet hedging idea that you can have portfolios of food choices or stocks that differ in both mean and variance. So you could say, like, I'm going to make certain foraging decisions today that give me this blue curve. And this blue curve has a higher mean. So on average, I will do better than this alternative foraging strategy over here. But this alternative foraging strategy that has less calories on average at the end of the day also has a lot less variance. And so, although it's very possible for my blue foraging strategy to give me very high returns, it also opens up the possibility that I'm not going to survive. So now we introduce this idea of basically animal insurance. So I thought I had that written here somewhere. So that, how do animals buy insurance? They, similar to paying for insurance, they choose a strategy which reduces their mean. That's like them paying someone to reduce their risk exposure. So they're saying, I could have behaved this way, but I'm going to sacrifice this amount of mean. What do I get from that? I get from it is a distribution of outcomes at the end of the day that is very tight. So it helps me guarantee survival. And that's what we refer to as bet hedging, tolerating lower average performance in order to reduce your exposure to risk. And we see examples of bet hedging all the time. There's one suggestion that the reason ants and honeybees engage in altruistic behaviors is that they're bet hedging, in that instead of focusing entirely on the average returns from your own fitness, you help your sister. And the amount of helping behavior of your sister goes beyond your basic relatedness because of all the variance that's out there in the world. So you're kind of diversifying your portfolio to reduce risk, even if it means investing less in yourself and less in your average rewards to yourself. So bet hedging has been used to explain a lot of things in plants, a lot of things in animals, and so on. So it's an important idea. Questions about that idea, what we mean by bet hedging, how we're choosing foraging behaviors that may sacrifice mean, but shrink variance. Well, the idea here is, if your average behavior is on average, I survive, I want to minimize my exposure to the rare possibility that I might die. So if my average behavior is in the survival behavior, then I can say, well, how do I get rid of this little portion of this blue curve that is in the death area, the below threshold death area? And somebody say, well, you can change your foraging behavior to make your rewards more consistent, but it comes at a cost. And that cost is the average rewards you're going to get at the end of the day are going to be less than the average rewards you get with your riskier scenario. So that's the idea, is that you're giving up on the average, how well. So every day, like Monday, Tuesday, Wednesday, you go out and you forage. you get 50 calories into the day. You get 55 calories the next day. You get 45 calories the next day, and so on. So this distribution is across all the days of foraging. How many calories do you get? Most of the time, you get the whatever 30 calories you need to survive the night. But some of these days, you only get 25 calories and you die. And so that's so important. That is a major hit to your fitness, death. So in order to, reduce death probability to zero, you might say, well, I'd really like to just get 40 calories every day. I don't care if that means that sometimes I don't get 45 calories, sometimes I don't get 46 calories, 47, 65, whatever. I'm okay with 40 because 40 is high enough for me to survive. So I'm taking a hit in my average behavior at the end of every day in order to guarantee that every day I am above the threshold. Any questions about that? And so birds like the yellow-eyed junco, they behave in ways that are sensitive to risk. So as you starve them, they change their behaviors in ways that embrace risk in some regimes and reduce risk in others. Okay, so that was from last time. If we dig back even further to the lecture before that, and I'm not going to go back into all these details, but there's not just time limitations and calorie limitations, there's also nutrient limitations. And we talked about this sloth and the algae that covers it and how it depends on that algae for nutrients that it does not get from its leaves. But the only way it can maintain that population of algae is by expending a huge amount of energy climbing down a tree to poop. And that process ends up raising larvae of moths that lead to moths, which die in its fur, which through the process of fungi breaking them down turns into algae, and so on. And so in this case, we see nutrient constraints, nutrient limitations, creating very weird behaviors in the sloth. So I want to investigate that a little bit further with some further examples of that. So this is sort of a famous example of these moose that Gary Bolovsky studied. And so this was back in 1978, he built a computer model that said, all right, so we've got these basic math models that were starting to emerge for optimal foraging theory. But he said, well, what if energy and time, that's not enough to explain all the variation that we see in foraging behavior? And he would notice that these moose were much more generalists than you would expect. So when you look at the things that they eat across aquatics, leaves, and flowers, forbs, then they eat a lot more of these things than you might expect. So if you look at the things that they eat here, you saw them eating these aquatics, these little things that come out of these ponds and streams and so on. These are really bulky, and they have the same amount of energy as leaves from trees that are much more accessible and not as bulky. But you still saw them eating them. And he thought that was weird, and it doesn't seem to be something you'd predict from these optimal foraging theory models. So he built a computer model that included all of this detail about all these diverse, like all the nutrient detail of all these diverse things that moose could eat. And he added in his modeled moose, a sodium limitation. So he's saying that kind of like the junco needs a certain amount of calories to survive at the end of the day, he was saying that the moose physiology, to do all the things that a moose gut needs to do, it needs a lot of salt. It needs a lot of sodium. And that sodium may help explain the generalism that you observe in this animal. So he built this model, ran the model, and got results that look like these. So these are the model's predictions with the sodium limitation, and these are the observations of a real moose that he studied here. And they match like perfectly. And when you run his model without a sodium limitation, or when you run his model basically based on optimal foraging theory ideas where it's only energy and time, way off. So sodium seems to be driving this moose to, these aquatics, these are extremely bulky, very low calorie content, and yet they're 18% of their diet. So it seems like this moose is doing a really weird thing if we only think in terms of calories. But if we expand and think in terms of the other micronutrients that are necessary for the moose physiology, then we start recovering what real moose are actually eating. So nutrient constraints drive weird behaviors. That's the kind of key message here. And we can see that not just with nutrients like salt, also with water. So this was done here at ASU. John Sabo, he's now at Tulane. Still work with him on some things, so he still comes back to ASU. And it was a cool project. He would study these riparian, so these food webs that are near streams or slightly farther away from streams. And in this case, he was focusing on these spiders, these wolf spiders, and they would see how often do wolf spiders eat field crickets or eat other smaller wolf spiders. And if you look at the calories here, so in this control case here, when they're so he basically set up these two treatments, one where you provide water and one where you don't. So if you imagine these spiders are living down by the river, a river system, then they have plenty of water. But if they are in another, where they're water deprived, then maybe that might change their foraging decisions. When you give them water, then what you find is that they end up eating, I think I might have flipped this here, but oh yeah, right. So the idea here is that when you give them water, they will eat small wolf spiders because that ends up being a better source of their, that's a better source of calories. This is like what you'd expect from normal foraging models, is that when you provide them extra water, free water, then they'll go and eat spiders. But in their natural environment, where they don't have as much water, when they're living farther away, then they flip their preference and they eat field crickets. And so the thought here is that even though the field crickets are poor sources of calories relative to how big they are, they're like juice boxes. So the spiders are drinking from their prey. So they're getting dietary water, and that's driving their food choices. And that explains these apparently weird behaviors in these spiders. This is what optimal foraging theory would predict, where they primarily will eat these spiders, and we can recover that if we give them enough water. But if we limit their water as they are in their natural environment, then they flip to eating animals that are filled with water, which I think is kind of cool there. So the juice box explanation. And then the last thing I want to talk about here as we close are these molluscivores, so mollusk-eating shorebirds, like these red knots. And so they eat these mollusks. Do you think they get much out of the shell? Does anybody, I mean, when you eat, if you are a shellfish eater, do you actually eat the shell? No, you don't have the guts for it, literally. They do have guts for it, but it's a limited capacity. So they have a gizzard, and that gizzard helps them process all of this shell, so that they eat the whole thing, and then the gizzard breaks down the shell, and then that helps them extract the meat that they end up needing. But that gizzard is a small piece of machinery, and it has an intake rate that can be used up. And when it's used up, they can't eat any more of these things. And so the thought was, maybe this could explain some of the choices that were observed that were violating optimal foraging theory for these red knots. And so I'm not going to go into the details of it, but they built this new model that considers the energy intake rate, remember watts, so that's like gain per time. So that's like your profitability over here. And also ballast intake rate on this axis here. And to make this line is sort of all of the kind of, it separates the kind of accessible choices from inaccessible choices. So again, I don't want to go into the details. I'm not going to ask you to do one of these analyses. But the point here is they created this modeling format that puts profitability on one axis and intake rate on the other axis. And if you assume that there's no digestive constraint, then it degenerates into optimal foraging theory. So this optimal diet line, that separates the food you eat from the food you don't, and it's a 0-1 relationship. But when you add the digestive constraint in, down here, if you say we do have a digestive constraint, then the model prescribes a recipe for how to pick the optimal diet for this gizzard-containing animal, for this intake rate constrained animal. And it ends up shifting this optimal diet line so that all of these dots, and these are things that it could be eating, everything above the line it eats, everything below the line it ignores. And in this thing, which takes into account ballast intake rate, you get a violation of the 0-1 rule. In fact, some of the prey you flip a coin to eat. So this is saying the optimal behavior when you come upon a shell, a mollusk that has a really big shell and a little bit of meat, is you have to consider the meat to shell ratio. And based on that meat to shell ratio, you flip a coin and say, do I eat this one or not? And if 75% of the time you eat it and 25% of not, then you're going to notice that the animal's going to sometimes ignore prey that if it encounters in the next second, it might eat. And that just comes out of the model. That's the predicted case. And if you go back to that belt experiment where they had the mealworms on the belt, they had partial preferences that were very much like that. So it's a thought that maybe partial preferences that you observe in nature are actually animals making decisions that are shaped by the small shape of their guts, so that the intake rate is shaping that as well. So constraints drive weird behavior. And in order to see all of these weird behaviors, we have to look across a lot of weird animals. And that's my kind of final big point from this lecture, is that some animals are water constrained, some animals are gut constrained, some animals are sodium constrained. We might expect different foraging patterns for all, but what everyone's looking for is the one theory. They're like physicists. They're looking for the unified theory, where if you know the constraints, you can predict things. And I'd say we're doing pretty well so far in the state of the art. All right, that's all we covered today. I don't want to keep you much longer, so let's just give you the question here, which I kind of already answered. So poll, multiple choice, A or B. So the idea here is why might an optimality model predict that humans should serve salad alone before other option? Is it because the salad is low profitability to other food or high profitability to other food? And we'll be talking about something else next week, Unit G. So have a good weekend. Okay. All right, I'll take a look and I'll post something into the chat or the announcements. No, that's good. That's excellent. I always forget to check those, and so if you can do that, that's very helpful.